Hello there. This is the final one on measures of location and spread, the fifth video of 5 on this topic, where we're going to be wrapping up standard deviation and having a closer look at how data can be coded. So sometimes you might have some data which is really awkward with massive numbers or numbers of decimals, which would make it quite easy for you to mispress when entering on your calculator. So sometimes data may be coded to make it more manageable than uncoded at the other end. I'll explain that towards the end of this session. But for now, if you can have a look at these warm-up questions. So as ever, there's 4 to be going on with, so here they are. And so if you can pause the video now and try these on your own, and then play the video to see if my solutions match your own, and make any corrections if necessary. Okay, so let's have a look now at warm-up question 1. So for question 1, we have to find the value of x such that 49 to the power x plus 1 equals root 7. Knowing what to do with these questions just comes with experience. And so the tip here is to spot and look at the numbers. So we've got 49 and 7. The thing with experience you spot is that both these numbers are powers of 7. And so the first step is to try and rearrange this equation so we have everything in terms of base 7. So first of all, I'm going to rewrite 49 as 7 squared. So 49 to the power x plus 1 is the same as 7 squared to the power of x plus 1. And in the same way, if you square root something, that's the same as taking something to the power of a half. And so for this first step, all I'm really doing here is just changing the 49 and rewriting it as 7 squared. Next, we need to remember the laws of indices. So we've got 7 to a power, then to another power. So it's 7 to the power of a power. If you've got 2 powers right next to each other, to work out the overall power, we multiply one power by the other. And so squared, then to this power, is the same as 2 times x and 2 times 1. And we leave the 7 to the half as it is. Next, we need to make a spot. So we've got something which is equal to each other. So one side's equal to the other. The base numbers are equal. Therefore, the only solution, the only answer to this is that if these powers are also equal. If the bases are equal, one side's equal to the other, these must be equal as well for it to all work. And so the next thing we need to spot is that this 2x plus 2 must be one and the same thing as this half. So that's what we can write down. So 2x plus 2 must equal a half. Now we just solve this easy equation. So hiding within here was this easy equation for us to find. So subtract 2 from both sides. So 2x is going to be minus 2.5, which is minus 5 over 2. We can put minus 2.5 if you wish. In fact, that's wrong, isn't it? Hold on. Dear. Sorry, first thing of the morning here. So half take away 2, that's going to be minus 1.5. That's minus 3 over 2. Or minus 1.5 if you want it to be. So therefore x, divide both sides by 2. X needs to be minus 3/4. So how could you check this on a calculator? Well, what we could do is actually input this value of x onto a class whiz. So if we have our class whiz here now, make sure it's back in the normal mode, so menu option 1. So let's try. So I'll just make the screen bigger for you so you can see it. So 49 to the power. Now we think it's minus 3/4. So minus 3/4 plus 1. And we get this here, this awkward decimal. So we get 2.6457. Let's now compare this to root 7. and you can see it is the exact same answer, 2.6457, and so on. So we have got the correct solution. Next, part B, a very similar question to part A in a sense. So again, it's a case of just experience to spot what to do. So here we've got numbers 16 and 4. We can change both of these numbers into base 4, because 16 is the same as 4 squared. We can then move this 4 to the other side. So we have 4 to the power 3x minus 2. So if we add on 4 to the power 3x minus 2 to both sides, we get this. So we can now see as well that both sides are equal to each other. The base values are the same. Therefore, in the same way as part A, this 2 must be the same as 3x minus 2. Add 2 to both sides. 4 equals 3x. Then divide by 3. X is going to be 4/3. And again, you can try this on a calculator by subbing in x equals 4/3 into this expression for the power. So if you type in 4 to the power 3x minus 2 with x replaced with 4/3, this should give you 16. In other words, this should give you 4 squared. So here's what I put in the calculator earlier. So if we press equals now, what we should see, hopefully, fingers crossed, is 16. And of course, yes, we do. So again, you can always check on the class quiz if your answer makes sense, if your answer is valid. Question 2. A bit of contextualized Pythagoras with some surds thrown in. So show that AC equals 2√5. So this is just a question of Pythagoras and also a way of revising, manipulating some surds. So AC squared would equal this one squared plus √3 plus 2 squared. So to work out AC, we just square root this whole thing. It's going to be the square root of 2√3 minus 1 squared plus whatever √3 plus 2 squared is. All of that summed and square rooted. So 2√3 minus 1 all squared. So we square 2√3. So 2 squared is going to give us 4. √3 squared is obviously 3. We then do the product and double it. So 2√3 times minus 1 is minus 2√3 and double that. So we have minus 4√3. And square the end thing. So square minus 1. Minus 1 times minus 1 is plus 1. So all I'm going to do here is say from this bit, we end up with this. And then from this bit here, √3 times √3 is 3. Double the product, so √3 times 2 is 2√3. Double that is 4√3. And finally square the 2 at the end, so 2 squared is 4. So that's what we get there. Again, it's all about square rooted. So now let's see if we can make this a bit simpler. So here we've got 4 times 3, which is 12, plus 1 is 13, plus 3 is 16, and plus 4 is 20. So this gives us 20. But now we have these 4 √3s to deal with, which is going to be a pain, isn't it? Or is it? Well, here we've got 4 √3, which is positive. That's going to cancel exactly with the minus 4 √3. So actually, though this looks really awkward, we just end up with exactly √20. The answer here is a clue. we've got it in terms of root 5, and 5 is a factor of 20. So we can change the root 20 into saying it's root 4 times root 5, because 4 times 5 is 20. But of course root 4 is 2, so we can replace root 4 with 2, leave root 5 as it is, and out pops the answer we wanted all along. So therefore, AC is 2 root 5. Question 3. Solve 4x to the power 4 plus 7x to the power 2 equals 2. Look at the powers here. One power of a variable is double the power of the other variable, therefore this is known as a hidden quadratic. So we need to know how to spot these. This is a hidden quadratic. You can always spot them when you've got the same variable and one power of it in one instance is double the other power of it in the other instance. So 4 is double 2, hence hidden quadratic. There's a few ways of solving these. This is my preferred method I'm going to show you. Make a substitution for the lesser power. So let big X replace x squared. So all I'm going to do here is this x squared is going to be replaced with big X. Now, x to the power 4 is the same as x squared times x squared. X squared times x squared is the same as big X times big X, which is the same as big X squared. So this x to the power 4 we replace with big X squared. 7x squared becomes 7 big X equals 2. We now can rearrange this. So it's like that. Now the examiner will want to see some algebraic manipulation to see that you can actually understand how to solve things by understanding. But I will show you how to do this on a class quiz as well. So at this stage here, so just ring around in blue. This one at this stage could be class quizzed. But let's imagine we live in a world where I grew up and these lovely calculators that you have don't exist. So we need to factorise this if possible. So we can use the AC method. So we do 4 and multiply it with a minus 2. 4 times minus 2 is minus 8. So what we need here is two numbers that multiply together to give us the minus 8. And when we add them together, give us this 7 in the middle. So if you wonder where the 7 comes from, we'll just highlight that for you. So now, a bit of brainstorming. Can you think of two such numbers that would make this work? Have a think. So the numbers that would work, I'm hoping you agree with me here, would be positive 8 and negative 1. So now what we can do is we can rewrite this one as 4x squared positive 8x minus 1x from this AC method we just applied minus 2 equals 0. We'll now have two different parts which will factorise themselves. Okay, so looking at this first grouping here, 4x squared plus 8x, that will factorise. We've got a common factor of 4 and a common factor of big X. So we can factorise out a 4 and a big X by having in brackets x plus 2. In a similar way, these pair here at the end will also factorise. Both terms are negative, so we can factorise out a negative 1. In the brackets, to make it work, we'd have x plus 2. So these beginning bits of both brackets form together to make their own bracket. So we put the 4x and the minus 1 together into the first bracket and leave this repeated bracket, which will always happen, on its own in the second. So now, if 1 times the other equals 0, either this bracket is 0, in which case for big X would have to equal 1, or if this bracket is equal to 0, we must have it where big X is equal to minus 2. And at this stage, we need to remind ourselves what big X actually was. The equation wasn't in terms of big X. The variable to solve was normal little x. Big X is x squared, so let's just now replace it and go back to the original variable. So 4x squared equals 1, or x squared equals minus 2. So now we need to be thinking logically. Can we ever have a number which after squaring it gives us a negative? This is absolutely impossible. By squaring a number, we force it to be non-negative, and so there's going to be no roots from this part here. So we can just cross this off and refuse to deal with it, because this is going to give us no real roots. The answers, the roots, are going to come from this bit here. So let's continue here. So if we divide both sides by 4, we get x squared equals a quarter, then square root, and remembering to take plus or minus roots. So the square root of a quarter is a half, so therefore x is either going to be minus a half, or x is going to equal positive a half. And we're done. However, I did mention to you that we could have class whizzed it at this stage over here. So I'm going to show you how to just shortcut it and also check your answers on a class whiz. So get the class whiz ready to go, switch it on. Now we need to press menu, and we scroll along until we get to equation/func. So press this one here. We're not solving a simultaneous equation. This is a polynomial, so press option 2 for polynomial. The degree of this is degree 2, because the highest power of the variable is 2. It's something squared. So press 2. Now we type in the coefficients as they appear, but bear in mind the equation needs to be in the form ax squared plus bx plus c equals 0, which it is, so we're good to go. So the x squared term, I'll make this bigger actually so you can see it if you're struggling to see what's going on in that smaller screen. So we type in, this one is 4, press equals. This one we type in 7, press equals. And the last one is minus 2. So type minus 2 and press equals. Then press equals again, you're going to get the first root. So root 1 is a quarter, but bear in mind this is what big X is. So either big X is a quarter, press equals again. The second root is that big X equals minus 2. So you can jump straight from here down to this stage using the class whiz. The rest of it is up to your understanding and hard work, of course, but that's a big skip. You don't have to do the AC method or any of this. It bypasses all of that, unless the examiner obviously asks you to say use algebra or show all working. So it's always safer to show how you know. But this is a really easy double check to go from this straight to that. Just another example of how the class whiz makes your life much easier. Final worked example, question 4. Express 70 plus 40x plus 5x squared in the form a brackets x plus b squared plus c. This is just a fancy way of asking you to complete the square. First of all, what I'm going to do is I'm going to rewrite this in descending powers of x. So we have 5x squared plus 40x plus 70. Now, if we're going to complete the square, the coefficient of the x squared needs to just be 1. So we need to get rid of this 5. So we get rid of this 5 by factorising it out. Note here, this isn't an equation, this is an expression. So we can't just divide by 5 because we'd be shrinking it by a factor of 5. If it was an equation, we could divide by 5 on both sides, but because there's only one side, we can't do that. So what we need to do is factorise out a 5. And so when we do that, we can have x squared plus 8x. We can leave this plus 70 on its own. We could have factorised that if you wanted, but I think it's easy just to leave it outside. The main thing is we deal with the variable terms, the x squareds and the x. We can now complete the square on this thing in the brackets. So you get big squared brackets up. So x squared, we write x. We halve the coefficient of the x, so plus 8 becomes plus 4. We square that, and then we minus off the 4 squared. So 4 squared is 16, so we minus 16. And again, don't forget the plus 70 at the end. So the main thing here is we've taken this and put it in this completed square form. So now we expand back out. So we've got 5 lots of x plus 4 squared minus 5 lots of 16. So 5 times minus 16 is minus 80, then plus 70. So finally we have 5 brackets x plus 4 squared minus 80 plus 70. Overall, that's minus 10. And that's all we need to do for that one, so that's the warm-up done. So let's move on to the main portion of this lesson. So we're going to be having a look at coding data. So data can be coded, and this example one is going to show you how we could code such data. So let's have a look at an example of data values. So consider the set of data values A as follows. So you've got 3 million, 4 million, 5 million, 6 million, 7 million. Just imagine now putting that into your calculator. You're typing in a lot of zeros there. You're typing in 30 zeros altogether. So if you just miss one, and you have to calculate the standard deviation or something, it's going to be really likely you mispress. You might not, but it's very likely that you would if you're not careful. So how could this be made a bit easier? What operation could we perform on this data to code it, if you like, into set B? So we've got A, could we make it into a more manageable set B, where set B's got more manageable values? But if we did that, what effect would it have on the mean and standard deviation? So just be thinking what we could do to these values to make them more manageable. So what operation could we perform? What coding could we make? Have a think and see if what you're thinking is on the same lines of mine. This is what would be a good idea to do. Divide all values by 1,000,000. If you divide all values by 1,000,000, this would just make them much, much easier. If we did that, the set of data values for B would just be 3, 4, 5, 6, 7, which couldn't really be easier to work with. If you took away 3 million, then you'd still be talking about millions. If you divided it by anything else, you might get awkward decimals. Divided by 1,000,000, with practice you can see what to code them with, but that just makes it much easier. So what would the effect be on the mean? So let's let you actually calculate the mean of A and the mean of set B. Okay, the mean of set A is 5 million if you work it out, and the mean of set B is 5. So the effect that's had is the mean's been divided by 1,000,000. The mean's been divided by what you divided the whole data set by. Think about now the standard deviation of A and the standard deviation of B. Feel free to pause the video at this stage and work this out yourself. Work out the standard deviation of set A, and then work out the standard deviation of set B, these values. I'm going to show you now what you should have got. Round it to 3 significant figures, if in doubt. The standard deviation of A was about 1,410,000. The standard deviation of B was 1.41. So again you can see, to go from A to B, the standard deviation has been divided as well by the same factor of 1,000,000. So what can we conclude here? Well, in summary, in this particular case, if data set A is coded into set B, where B is A over 1,000,000, then the mean of B gets divided by 1,000,000, and the standard deviation also gets divided by 1,000,000. So make a leap of faith and be thinking, what would happen if we divided by any number? If it was divided by 5 or divided by 10? Well, the same thing would happen. If you take a data set and divide it by a constant, then the mean and the standard deviation of the original data set would be divided by that same constant. Let's have a look at a second worked example. Again, just trying to use some intuition here. Consider this different data set. Consider this time the set of data values P, where P is 3,000,001, 3,000,002, 3,000,003, 3,000,004, and finally 3,000,005. So again, asking you the same question, what operation could we perform on P to code it into set Q, where Q's got more manageable values? So you might be thinking, well, I could divide it by 1,000,000 again. But if you did that, you'd have just really long decimals. You'd have like 3.000001. So dividing by 1,000,000 wouldn't really get you very far. Have a think and press play when you think you've got it. Okay, I would suggest the coding may well be that we just take away 3,000,000 from all values. That then transform P into this set of values Q. Q would then be 1, 2, 3, 4, 5. Work out the mean of P and the mean of this new set Q, and then think about what effect it's had by subtracting 3,000,000. So pause the video now and just calculate this yourself. Okay, if you've done that, let's see if you agree. So the mean of P was 3,000,003, whereas the mean of Q is just 3. So the mean's been shifted by minus 3,000,000. We've taken away 3,000,000 from the original mean. So if we subtract a certain number or add a certain number to all values, the mean is changed by that same factor. But this is the main thing. What effect is going to happen on the standard deviation of P and the standard deviation of Q? So what effect does it have by performing this subtraction? Try that now on your class whiz. Press play when you've tried it. Okay, this might seem weird, but the standard deviation is completely unchanged. But let's just think about what the standard deviation is. It's a measure of the average spread away from the mean. Okay, so look at this data here. For Q, the mean was 3. How spread out is, for example, 1 from 3? That's 2 away. 5 is 2 away from the mean. 2 and 4 are 1 away from the mean. This original data set, the mean was 3,000,003. The lower value was exactly the same distance away, just 2 away, as 1 was from 3. 3,005 is also exactly the same distance away from 3,003, just a distance of 2 away, as 5 is from 3. So the spread doesn't change, because all data points are moving together relative to themselves for no further or closer together than what they were to begin with. So what's the conclusion from this? Well, the summary is if data set A is coded into set B, where B is A minus 3,000,000, then the mean of B is a mean of A subtract 3,000,000. But the standard deviation, this is really important, is not affected by shifting the data by some constant. So if we take a data set and add something to it or subtract something, the standard deviation isn't altered. The standard deviation is only affected when we multiply or divide a data set by a constant. So let's try and summarize these results and generalize them too. So from those couple of examples, we've seen that the effect of dividing all data values by a constant has the equivalent effect of dividing the means and standard deviations by the same constant for the new coded data. However, adding or subtracting a constant to all data values affects the mean of the coded data by the same constant, but it has no effect on the standard deviation. No effect at all. So we can also link these two ideas together for when elements of a dataset are increased or decreased by a constant, A, and divided by another constant, B. So here are the general results in a nice lovely yellow. So, if data is coded using the formula, the new data y is the old data x minus a, then divided by a constant b, then the mean of the coded data is given by mean of y is mean of x minus a over b, because the mean is affected by the shift and the division, whereas the standard deviation of the coded data, like we saw before, is not affected by this plus or minus a, because it's only affected by dividing or multiplying by the b. Standard deviation of y is just a standard deviation of x divided by b. So this a, or the minus a, has no effect on the standard deviation, so we drop this from the formula for rearranging for the standard deviation. As well as this, we're often asked to decode the data at the other end to work out the mean and standard deviation of the original data. So this is done by a simple rearrangement of these formulae here. So what we'd have is if data has been coded into y from x, so y is x minus a over b, the mean of the original x, multiply both sides by b, then add on a, but sigma x is just going to be b sigma y, and we get this by just rearranging not this formula here, but by rearranging this one up here, because again you need to remember when we're talking about standard deviations being coded, this a essentially you can imagine is invisible, doesn't exist because it's not affected by the a. So that's really all there is to it. It's now just a case of practicing and showing you with some worked examples how this works in practice. Let's take a look at a worked example with coding data. So we've got this data set M given below, so quite big awkward values. So we need to use the coding n, where n is m minus 5 million divided by 100 to code this data. So we can use a calculator, I'd suggest for this one. So part A, I'm just going to subtract a million from each value. Sorry, subtract 5 million from each value, I mean to say. Then we're going to divide by 100. And so n is going to look quite a bit different from m. So this one, take away 5 million, divide by 100, that's going to give us 3. This value here will be 2. Over here, subtract 5 million leaves us with 100. Divide 100 by 100, that's going to be 1. This one is going to be 9. And finally, this one at the end will just be 5. So now, I'm going to calculate the mean and standard deviation of this coded data. So what I'm going to do here, I'm going to jump straight to the class whiz for this one. So straight on the class whiz, let's press menu, go to 6 for statistics, 1 variable calculation, and we're good to go. Now, this frequency column you might have, if that's freaking you out, you don't need to use it, of course, but you can make it disappear. I'll show you how, because it's not a frequency table, we don't need it. So if you press Shift menu, scroll down to statistics, press option 3, press 2 to turn frequency off. And there you have it, we can just put them in one by one now. So the first value is 3, press equals, 2, press equals, 1, 9, and finally 5. Now press AC to clear, then OPTN, option 2, 1 variable calculations. So to make it bigger so you can see it, what we've got here, we can see the mean is 4, and the standard deviation will give us to 3 significant figures. The standard deviation is 2.85. 3. So let's just pop this value in. So the mean for n is 4, and the standard deviation, I'm going to do this as subscript n, so I don't get confused with m. So that was 2.83. Now for part C, it says use your answer to part B to calculate the mean and standard deviation of the original data. So now at this point, we might need to remember the formulae we saw earlier for how to code back to the original. So just to remind you, I've got this here. So we can work out the original data by multiplying by B and multiplying by A, where we have this formula here. So we just need to change the variables from X and Y to obviously M and N. So using this idea here and adapting it to our particular case, we can work out the mean of M. So mean of M is going to be the mean of N multiplied by what we divided by. So we divided by 100. So it's going to be 100 lots of the mean of N. Then we're going to plus whatever we subtracted from it. So we need to add on 5 million. So if we did that, 100 times 4 is 400. 400 plus 5 million is going to be 5 million and 400. And the standard deviation of n, this is where we just multiply it by what we divided it by. So we divided by 100, so we multiply the standard deviation of m. So I got these figures the wrong way around. M is what we're trying to find out. My apologies. The standard deviation of m is 100 multiplied by the standard deviation of n. So 2.83, multiply it by 100. The standard deviation of the original data was therefore 283. So look at a second worked example. This time a scientist is measuring the temperature, X degrees, at 5 different points in a nuclear reactor. So her results are given below. So again, similar to worked example 1, part A, user coding y equals x minus 300 divided by 10 to code the data. So I'm going to call this coded data y for part A. So part A, call the coded data y. So take away 300 and divide by 10. This one will be 3.2. Again, check with a calculator if you want to be safe. This one, we have 55 divided by 10, that's 5.5. This one becomes 0.6. This one would become 1.7. And lastly, this one would become 4. Part B, calculate the mean and standard deviation of the coded data. So what we want here, we want to work out y bar. The mean of the coded data is y. So here's where we can use a class whiz again. So if we go to menu, option 6, we get into statistics, one variable. Is that all the data we had? Is it up to 4? Yes. So we've got 5 different data points. Just check we're not missing any out. So what we need to do now is to input the data. And so what we're going to do for this one is we're going to go for OPTN. Oops, hold on a second. So menu, let's do this step by step. So menu, we want option 6, one variable calculation. So press 1. So now just input the data step by step. So 3.2 equals 5.5 equals 0.6, 1.7, and then 4. Press AC to clear it. Now OPTN 2 for one variable calculations. So just to make it slightly bigger for you if you'd like. So the mean is 3. The standard deviation to 3 sig figs is 1.72. Standard deviation of the coded data is 1.72. Just check we've got that one right. Yes, we do. So then part C, again similar to worked example 1, just using what we have already, calculate the mean and standard deviation of the original data. So at this stage again I'm just going to remind you of the formulae we had, which will be useful. There they are. So the mean for x is going to be what we divided by multiplied by the mean of y. So 10 lots of the mean of y plus what we subtracted. So plus, in this case, this 300. So 10 times 3 plus 300, that would give us 330. So the mean for x, the mean temperature here, was 330 degrees Celsius. And the standard deviation for x is simply the standard deviation for y multiplied by what we divided by. Our b, in this case, is 10. So multiply the standard deviation of y by 10. So 1.72 multiplied by 10 gives us 17.2. And because we've returned to original data, we've returned to the original units, which were in degrees C. So we can put in degrees C for this one. Finally, worked example 3. So this is from the large data set, which I'll mention in another future video. But anyway, we don't need the large data set now to understand this. I'll talk you through it. So data on the maximum gust. Gust is like a type of wind speed. G knots is recorded in Luchars during May and June 2015. So the data was coded using h equals g minus 5 divided by 10, and the following statistics were found. So this here is the data for what was coded. This isn't the original. This is in terms of h, not g. So calculate the mean and standard deviation of the maximum gust in knots. The first question you might be thinking is, what on earth does subscript HH mean? Why not just H? Why double H? I'll explain this to you. It's much easier than what it might appear. So all this means here is it's called a different summary statistic. And so the standard deviation in terms of the variable h is just this HH divided by n. This has been taken in this little box from the official data sheet and formula booklet you'll be given in the exams. So sometimes you can have bivariate data where there's more than one variable. So the fact it's subscript with the same letter is just denoting that the only variable here we're talking about is h. Not, for example, h and g or x and y. It's just h in this case. So as you can see here, all we need to do is actually take this thing here, divide by the number of data elements and square root to find the standard deviation of g. Okay, so sorry, that's for h. And to go back to g, we use this coding formula. So what we can do here, using this idea, is we can work out the mean of h, which we already got actually, so we can now work out the standard deviation of h. So it's going to be this thing here divided by n, which we've been told as well, then square rooted. So it's going to be the square root of 43.58 over 61. And we can give this to 3 significant figures. So go back to the calculator, press menu 1 to go back to normal mode. So we got the square root of 43.58 over 61. So to 3 sig figs, that's 0.845. I'll also mention here that the mean of h is given as 2. But we want to work out the mean and standard deviation of the maximum gust in knots. So if we're working out maximum gust in knots, we want to work out the original data, which was g. So we need to uncode it. So what we need to do now is to go back to what g was by a rearrangement of this formula for how we got h from g. So again, what we need to do is remind ourselves of these two formulae for going back. So we can now therefore say that the mean gust in knots, the mean of g, is going to be what we divided by, which is 10, multiplied by the mean of h, plus 5. So 10 times 2 so that 2 has just come from here, by the way. 10 times 2 plus 5, that gives us 25 knots. And the standard deviation of g is just going to be what we divided by, which is 10 multiplied by the standard deviation of h. So it's 10 times this, which to 3 sig figs again is 8.45 knots. And then we're done. So now it's over to you to practice these questions yourselves with some independent study. So here are the exercises I'd suggest. So page 33, exercise 2F, it's going to be questions 1 through to 3. I suggest to skip through to questions 6, 7, 8 and 9. So try those on your own. Let me know if you're stuck or struggling. If you are stuck or struggling, obviously you have to let me know either in class or on an email, or even leave a comment in the comments section. I'll do my best to help you out. Do subscribe to the channel, that'd be lovely. Do keep working hard, and do please see me soon. Thanks very much for listening, and bye for now.